In this video, we'll address now really the important issue, which is once you give me an n by n matrix A, if I know the eigenvalues, we've been finding eigenvectors using our standard techniques. But how do I actually know what the eigenvalues of a matrix A? And so we're going to address that now. So the following statements that I'm going to write down are all equivalent. T, F, A, E, the following are equivalent. If one of the statements that I'm going to write down is true, then all of them are true. And if one of them is false, all of them is false. And we're going to take advantage here of the invertible matrix theorem. And we're going to start by putting at the top that lambda is an eigenvalue of my matrix A. So lambda is some number, and if it's an eigenvalue of my matrix A, then it must be that if I look at the homogeneous equation A minus lambda I times x equal to 0 has non-trivial solutions. If that's the case, it means the null space is not zero-dimensional, that there's at least something other than the zero vector in the null space of that matrix. So the dimension of the null space of A minus lambda I, what we've been calling the lambda eigenspace, is non-zero in dimension. Well, if a matrix has a non-trivial solution to its homogeneous equation, it cannot be invertible. That would occur because there would be a column that would not have a pivot, resulting in a free variable, and you know that a matrix is going to be invertible if and only if it has a pivot in each row and each column. So A minus lambda I is not invertible in the case that lambda is an eigenvalue of A. And you have a straightforward computational tool for detecting whether or not a matrix is invertible. It's the determinant. And if we look at the determinant of a matrix that is not invertible, it should be 0. So lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. This expression right here is an algebraic equation in a variable that we call lambda. This is what's called the characteristic equation of our matrix A. If you solve this equation for lambda, you'll get the solutions, and those will be the eigenvalues of your matrix A. So now we have an algebraic method for determining what the eigenvalues are. I'm going to take an example here. I'm going to let A be the matrix 2, 3, 1, 4. What we're going to do is find its characteristic equation, and we'll find the roots of the characteristic equation, and therefore find the eigenvalues of our matrix. So I first need to begin by looking at A minus lambda I. That's a matrix. Lambda is an unspecified value right now. We don't know the eigenvalues. So I'm going to have lambda taken away from each entry along the diagonal, and the entries off the diagonal won't change. It'll be 2 minus lambda, 4 minus lambda, and then the 3 and 1 stay the same. The characteristic equation says calculate the determinant of this expression. So I'm going to take the determinant of A minus lambda I. This is a 2 by 2 matrix, easy to do the determinant by just doing an expansion here. I'm going to take 2 minus lambda times 4 minus lambda, and then I need to subtract from that 3 times 1, so minus 3. Let's just expand all this out, FOIL this out a little bit. I'll have 8 minus 6 lambda plus lambda squared minus 3. And then let's just collect like terms, putting things in order. Lambda squared minus 6 lambda plus 5. We want to know when this is 0. If this is 0, then lambda is an eigenvalue because it will make this matrix non-invertible, and therefore its eigenspace non-trivial, giving solutions to the homogeneous equation. So let's see if I can factor it. It's a quadratic equation, degree 2 equation in lambda. Hopefully it's nice I can factor it. And indeed it factors as lambda minus 5 and lambda minus 1. If it didn't factor nicely, I could of course use the quadratic formula to find the roots of that equation. But in this case we can easily read them off that lambda must be 5 or lambda equal to 1, and those are the two eigenvalues of this matrix A. We can now go ahead and find the eigenspaces that go with it if you're interested in doing that, but we've covered that already, so we'll leave it here. Let's look at another example. Here I have an upper triangular matrix. It has 3, 3, and 1 along the diagonal, so it is upper triangular. We already know that the eigenvalue should be 3, 3, and 1 by our previous theorem, but let's just test this characteristic equation approach. I'll take A minus lambda I. That means I need to subtract lambda along the diagonal, and along the for the other entries nothing changes. And then the characteristic equation requires you to take the determinant of this matrix. It's an upper triangular matrix, so the determinant is just the product of the diagonal entries. So I'm going to have 3 minus lambda, 2 factors of that multiplied together, and 1 factor of 1 minus lambda. And we set that equal to 0, and the roots are our eigenvalues, and because it's already factored for us, the eigenvalues are clear. It's 3, 3 from this factor as well, and 1. Notice what happens here is that if A is an n by n matrix, then this thing called the characteristic equation, the determinant of A minus lambda I, is going to be some big polynomial in this variable lambda. If it's a 3 by 3, we'll get a degree 3, something cubic in lambda. And our previous example was degree 2. We got something quadratic. Whatever the size of the matrix is, that will determine the degree of the characteristic equation. You try to find the roots of that equation, and its roots are the eigenvalues, but as we see here, sometimes roots get repeated. So in this case, we saw lambda equal to 3 occurred twice. So we're going to say that the number of times lambda appears as a root is called the multiplicity of lambda as an eigenvalue. In our previous example, lambda equal to 1 has multiplicity 1 because it only occurred once as a root to the characteristic equation. While lambda equal to 3 has multiplicity of 2 because it occurred twice as a root to the characteristic equation.